How's everybody doing? How's challenge 4? People looked at it yet? No. Okay. So, basic where we are. We're going to do hashing today. On Friday, we will kind of do a wrap-up of everything from the semester and talk about applying it. Next week, we will do a little more wrap-up, and we'll take a quiz on applying data structures, and then on Wednesday, we'll have an exam review, and Friday, we'll have exam 3. And your challenge 4 is due this Friday, too. So.
Yeah, that's rough.
All right. Challenge 4. Yes. Challenge 4 is the last challenge. Yeah. So that's good news. Last time we did talk about challenge 4 and how to set that up. There have been a few changes since then, and if you remember, we talked about this a little bit with the random number range being just 0 to 1,000. So the assignment has been updated. This is on Canvas now. And the update is to use the range 0 to 2 million instead of 0 to 1,000. So not a big thing, just change it in the code. Makes a lot more sense. With the code, the example code that's on Canvas, the version that I had uploaded initially had a problem with C++ 11. So I was using C++ 17, I think, and on one line of code I wrote a templating thing in the way that isn't supported by C++ 11. So I did fix that line of code and updated that, and the new version is on Canvas. So if you're running into a compiler problem and you want to use C++ 11, download that new version. Another fun thing that has come up with Challenge 4 is that when you do these last two parts of the challenge, which are to do the sequential adding of like 1 to 10,000 and then 10,000 to 1, depending on your environment, like your computer, your development environment, all of these things, you may get a stack overflow because the default size of the virtual stack seems to be pretty small on Windows by default. I think it's like a megabyte. Again, it depends on what you're passing to the compiler, but if you're using a development environment, it's taking care of that for you. So it may be setting that differently. You can increase that so that you don't get that stack overflow, but it does depend on your setup as to how you do that. So if you end up, when you're doing these last two parts of the challenge, if you run into the stack overflow problem, to make sure that that's what it is, instead of going from like 1 to 10,000, try just going like 1 to 2,000, which should fit in that smaller stack. And that'll let you know if that's the problem. Then you can, depending on what you're using, all you need to do is just search for how to increase the virtual stack size for your development environment. And it's pretty easy to do, like in Visual Studio. It's not too bad in Visual Studio Code. So you can look at that. But the TAs are aware of this. And so if worst comes to worst, and you can't get your virtual stack size increased, I think they will be okay with you showing them, just up to 3,000 or whatever works. And then they may also be able to help you up the stack size too. But again, it just depends on your environment. So
and how will I know if it's not working?
So it will, at runtime, it'll throw an error. And again, if you're running it like from an IDE, it will pop up and it will probably say like Stack Overflow at this line. If you're running it, just on the terminal, I'm not sure what the exact message will be. But the way you can test it is just to lower that number quite a bit, and then you'll know. And so, let me see. Let me briefly talk about those last two cases. So let's see. All right. So if you remember, we were doing these comparisons, and we wrote the first one. And so these last two are the ones where the stack thing can happen. But to write these, what we want to do, so for example, when we did the binary search tree, right, and we were doing insertions of the random numbers on it. So remember, we created the binary search tree here. And so in this case, it's called bcomp1. And what we did to insert elements into it, here we were just inserting, we made this array of random integers called comp array 1. For the case where we're just doing like 1 to 10,000 or 1 to 3,000 or whatever works, instead of inserting the value from the array, just insert I, so 0, 1, 2, 3, 4, just like that. And then for the last one, which is 10,000 down to 1, or 3,000 down to 1, whatever you pick, just the same kind of thing, for loop, but start high and go low. Are there any questions about challenge 4 that are jumping out?
I got a question
Yeah.
about, it said in the PDF that we're going to have to delete part of the randomization code. How much of the randomization code?
So I would be prepared to write all of it. And I would recommend, so in the code that we have, remember we have 2 random functions. We have this shorter one, generate random int array, and the longer shuffle one. Since they are testing, like memorizing things, I would recommend you just go with the shorter one, right? Because even though it's not as robust of a test, it's acceptable for this, and it is a bit easier to remember what exactly it's doing.
And what if they ask for the longer one?
They won't.
Oh, right, you're in charge of this.
So with this code, it's not like what you give us and then we like change stuff, or it's just like stuff we gotta like write on our own?
So you've got to write the test conditions on your own.
Do you already have them for us, or we gotta make it?
So they're in the PDF, and the first one is written for you as an example.
So we just go off the.
Yeah, you can look at so this first one is like right here, time comparison 1, and it goes on for a while. And then,
That's all of it? And we gotta do that for
yeah, it looks way worse because it's giant on the screen. But and then here are the ones that you need to do.
So what would change between those? Is it a lot?
No, it's just the number of elements in that you're putting into the linked list or the binary search tree. And then these last two are just, instead of doing random, you're just doing it in order.
The last two, we would just have to change the for loop to increment backwards.
Yeah, exactly.
What exactly is it supposed to look like whenever it's output?
Those are great questions. So up in this main.cpp, starting at line 86, this is the format. I just got it all in comments here because I know that this is not on the PDF. But essentially, this is the format that the TAs will be most familiar with, as long as you have this information of how much time it took for the linked list, the binary search tree, for each of the things, for inserting and for searching. That's what they want. And so I would just follow this format. And that's what the first test case outputs it like that too. But yeah, don't worry about the shuffle array thing. That is just for our section, just because I want you to know how to do this if you were doing this for real and didn't want the chance of having duplicates that would make the comparison different. But for the actual assignment, you should use the shorter one since you're going to need to be able to recreate it from memory. All right, other questions? Okay. Then we'll move on to hashing, which is our last new topic for the semester. Unless, did anybody think of anything they wanted to learn about data structures that we didn't go over? Any requests? It's not too late. Okay. If you think of it during class, or later, email me. So, if you remember when we started things, we were talking about kind of the most basic data structure that we all learn first would be an array, right? Or a list or a vector or whatever we want to call it. And it's just slots of memory, right? And one of the great things about just having slots of memory is that as long as you know the address of what you're looking for, how long does it take to find it? It's like instant, right? We just consider it order 1, right? Like, because hardware takes care of that and it's very fast. So if we know where something is and we can just get to the memory address, then that is pretty much the quickest way of getting there. The idea of hashing tries to leverage that a little bit and expand that idea out to be a little more practical. So we're going to imagine if we're storing data, whatever the data might be, imagine it having 2 fields, like a key and a value, always. And so this is pretty common. You'll see this, like a lot of languages, if you have an array, you can put like a string as the indexing thing, right? Instead of just an integer. You have dictionaries in some languages. And this is kind of like that. And so if you imagine that for any piece of data, whatever that data is, that you have some type of identifier for it, we can take that identifier and essentially convert it to a memory address directly, is the goal. So the idea being, like these examples, which works well with the green here, you have a key that's an integer, and then you might have like a string that might be your value. It could be a big object that could be your value. It could just be a pointer to something that is your value. Anything you want. And so you can imagine, we'll call this direct address tables, and it's the idea being, if we know this key, and the key is an integer, we can make this an array, right? We can index into the array. And so the basic idea is that accessing memory is fast if we know the address of what we want. And so with hashing, we are able to insert data, like save new data, update data that exists, find data that exists, and delete data all in order 1 time, which is the best you'll get. So this is kind of one of the most important things we have. So there are some obvious challenges here, right? So when you're thinking about like arbitrary data, and let's say you've got like maybe a string coming in that is someone's name, and like the data that's stored is, I don't know, their address or something important that you need, right? How do you take the string of a name and convert that to a number that is in your memory space, right? And that's the question we're going to answer. So the problem here is that the world of possible strings is large, like very, very large, too large. And we only have like a tiny amount of memory in comparison, right? We have some finite bit of memory. And so when we talk about all of the possible keys, all the possible things out there, we'll call that the universe of possible keys that exist. And when we'll talk about our memory, we'll call that a hash table. So kind of visually, the way that you can think of this is that you've got a universe of keys that you care about. And so in this case, these are just integer keys already. And so from that universe, there's some subset that you'll actually need to store and interact with in your software. And so the idea is that you want to be able to map any of these into this array-like structure. And so, just to give you a little bit of background about the word hashing. So it is something that came into English like in the 1600s, but it is from a French word. It essentially means chop up and mix up, and it's related to cooking. And so that is why it applies here, because what we are going to do with this key data is chop it up and push it back together and use it as an address. So we have a key value. So these are kind of the vocabulary that we'll need for hashing, which it's pretty good. So the key value is just that input to the hash function, and you can think of it as being any like sequence of possible bytes that exist in the world, any string of zeros and ones. More practically, when we look at it, we'll see it like as a word or a string. It could be anything though. So that is your input. We have a hash function that takes that input and converts it into a hash. And for us, a hash is an integer, and specifically an integer within our array of things that we can store. And so we have the concept of a hash or a hash code, you'll sometimes see it called, and that is that value that comes back from the hash function. Then we kind of store all of this in what we would call a hash table, and that's simply an array where the index is the result. We're indexing on this hash code to find our data. So visually, looking at it, you have some data, you take that data, it goes into this magic hash function, which will spit out some index within the array that you have here. So the big question is in kind of designing this magic box here, right? Because on one side of this box, you've got the whole universe of everything. And on the other side, you've got this array of M elements or whatever, right? That's kind of a big task to solve. So we take in kind of anything. Obviously, what we take in has to be finite in some way, but we get pretty much anything within reason. And we want to output a fixed size integer, which is the hash value. What's important is that the same input always gives us the same output. So anything that I hash, yes?
You using like modulus or something?
Yes, you're on the right track. Yeah, so as we begin to think about how we will get this into the array, yeah, we will be reflecting on modulus. So it's important that we always get that same output, right? I mean, because if we're going to use this like to say store something, then maybe look it up later and then maybe change it and then maybe delete it. If we don't get the same mapping every time, we either won't find it, we'll find the wrong thing, we'll do something, that we shouldn't do. So we can't do anything random in here, is what's important. It has to be built on the input alone. In general, we want to try to map these values across like our array, right, in a uniform way. We want to spread them out very nicely. Because while we have the rule that the same input always gives the same output, different inputs could give the same output. And that is what we would call a collision. And we'll see examples. But so when that happens, you're really kind of in trouble, right? Because you've already filled that slot, and now you've got something else that wants to be there. One side note that's really not all that important because it's easy. The actual computation of the hash should be quick. So here is our friend modulus. So as we start to build a basic hash function, we need to remember modulus briefly. So if you remember, you see something like k mod m, or k and a nice little percent sign m, that is simply saying take the remainder whenever k is divided by m. And so, for example, here is k and m set to 7. right? And k mod m, here's your results. Now, kind of the intuition here, you can see what's nice about this, right, is that no matter how high you go, you stay within that range that you set up, right? Whatever you set m to, you're not going to go over that. You're always going to be kind of just circling around, right? So when we talk about a hash function specifically, and anything could be a hash function, a really bad hash function would just like return 42 every time. It's still a hash function, but it's not good. Generally, the form of our hash function is going to be something mod something, and where the second something, mod m, we'll use m as the size of our table. Just so that's saying, we always want to stay within these bounds, right? If it goes way over, we need to loop back around. And so we'll use kind of notationally the key will be k, and m will be the number of slots in our table, and then h will be our hash function. And so you can see here, if our hash function were just k mod m, then this is the output we get for these inputs. So let's do a very, very basic hash function here, and we'll do it with a string. So I'll use ASCII representations. So if you aren't familiar, a long time ago, when we were building computers, we decided that we would give all of the letters in the English language a number to go with them, the ASCII encoding. This is not really something that we should use anymore. We now have encodings that allow us to do kind of like, all the character sets on Earth in different languages and not just like basic English letters. But for simplicity, we'll use ASCII here. And so what you need to know about ASCII is that each letter has a number associated with it already. So we'll define our hash function to be something very simple. In our hash function, we'll say our sum is 0. Then for each character in our string, we will add the ASCII value to the sum. And then at the very end, we will take the sum and we will do a modulus with the number of slots we have in our hash table. So let's imagine that our number of slots is 10. We just have an array with 10 slots in it. Let's imagine that our string that we get in is alpha. This talk is not sponsored by Wicked, but their advertising is everywhere, so it's working, I guess. But let's say that's the key. And so if we were to convert each letter, E, L, F, into numbers, we would get this, which will sum up to this. And so then we would end up taking 685 mod 10, we get 5. So we've converted our key, which was a string, into an integer, 5, which is now a memory location. And so now, whatever it is we wanted to store with this, we can put in that slot. And then later, all we need to know is the string to look it up. So if we were to do this for some other related strings, you would see that they would all kind of map to these different values. But there are some problems here. So you see the problems. Right, yeah, so we've got collisions, right? So we've got a couple of 2s and 5s and 1s. And so now we're kind of in trouble because we can't just we can't map this in a straightforward way. There's not 2 slots for these. So how do we deal with it? The first thought is probably to design a better hash function, which is a good thought, and we will. But I am here to tell you that collisions will happen. They might not happen very often, which is what we would hope for, but they will. So what we really need to do is kind of come up with more of a coping strategy here with what we do when we have a collision. And if we do it in the right way, it won't impact our overall average performance. So here's an idea. Let's say we've got our 5-slot array. Instead of just storing one thing in each index. What if we stored a linked list in there, right? So if you come through and your hash is 1, well, if you're the first one, you're the first member of the linked list. If somebody else is already there, we just tack you onto the linked list. This could be okay. It just means that when we need to look something up and it hashes to 1, we have to do a comparison on every element that's in that list still, which could still be better than other data structures, but it's could add up to be, on average, not that order 1 that we're looking for. And so as this list gets very, very long, if, for example, you had that hashing function that just returned 42, everything would just be in slot 42 in a giant list, and you'd be back to, order of n, however many items you had. So you'll also get some data clustering that happens depending on the hash function as well. So this is a solution that can work sometimes, depending on what you're doing, but it's probably not the best go-to solution. So another way we could do this is something kind of simple. We'll call it linear probing. So what we would do is we calculate the hash value, right, for whatever our input is. And if we get to that slot and there's something already there, right, then what we do is just increment by 1 and see if that slot's empty. If it is, we'll store our thing there and move on with life. And we'll just keep doing that. So this is nice because we don't need any extra memory or anything, right? We're just using the slots we allocated. But we've still got to kind of follow this path if we're going to find this element later, right? Because when we go to look something up and it sends us to a certain index and the thing that we're expecting it's not a match, then we need to increment and check the next one and so on. And you can see how this can either cost us more data or more time to do this. And so if we were to do it this way, as an example, right, let's say that we start from the top of these. So we have Glinda, which is index 1. So we will move it into slot 1. And then we have, let's see, No Good Deed is index 1 as well. So we would put it here, but if we're doing linear probing and this is full, then we're just going to increment by 1 and put it into 2. Alpha is 5, so that will be fine. There's nothing there. 4 is okay too. Now we have another 5. When we do that, we will loop around and end up putting that in 0. So this solves the problem a little bit, but again, we have to follow these paths if we're looking for something. And if you think about deleting something, we can't actually just delete something in the middle of this. We kind of have to leave a note because we need it as the next jump to check if something else is there. So this is an okay idea. It's not perfect. And it does bring up the question as we start to look at this. Obviously, the hash table has a finite size, and at some point, we will need to change its size. So in order to do that, we kind of use a concept. It's really basic. It's what you would think. We call it a load factor, and it's just the total number of entries in the table divided by the total possible slots in the table. And so that would give you a number 0 to 1. Sometimes people multiply it by 100 and make it a percent. Whatever you want to do there is fine. And we can use this factor to decide when we're going to change the size of the overall hash table. And so in general, if we're doing linear probing, we actually just wait until it's full. So it'll be a 1 or 100%, and then we would resize the hash table at that point. So for actually resizing the table, if we're growing the table larger, the way that we're going to have to do that is allocate the new set of memory, And then we are actually going to have to rehash everything that we had into the new table. Because if you remember, the hash function always depends on the table size, right? So the hash function changes when we change the table size. So that has to be recomputed. So this turns out to be doable in order of n time, and on average, this is negligible when we're using hashing and hash tables. So, and this is a lot, with hashing, most things that we talk about are amortized over time cost. They're on average, they are not worst case. But it does work that way. So when we resize, natural question is how much bigger do we make the table, right? So in general, I'll just tell you the answer is we want to double it. If we were to do kind of the other extreme, let's just say we add one slot each time, you can work through some proofs that I will not complicate your life with here, but trust me, it changes our runtime to order n squared, and we don't want that. So when we think about this, if we need to make it bigger, we're always going to double it so that we can keep that amortized constant time overall. So there's a good amount of number theory behind kind of all of this. If you're interested in that, this is a really fun topic when it comes to that. You can prove all of these things, and it is kind of an interesting set of material. So we should also talk about shrinking the table, because sometimes that would make sense, right? And I'll give you the answer here too, because it turns out to be a little bit to work through to do the proofs of this. But essentially, what you want to do is when your number of filled slots becomes a fourth of the total slots, then you want to cut it in half. And so that will keep you at that order one time amortized. There's also the question of how do we choose the size initially for a hash table. We do want enough space for whatever we're doing. We don't want more space than what we need. The answer here is to kind of pick a small constant, start there, and then just grow and shrink as you need to. And it depends on the application, right? So you just kind of can look at it practically. So we talked about two approaches to hashing, right? Mostly dealing with the collisions, right? And so those are obviously not the only two ways to do this. There are a lot of ways to do this. So we talked about the linear probing, and that is part of a subset of what we call open addressing. And that's just meaning that we are using the array we have and nothing more. We talked about chaining, which is that idea of putting like a linked list structure in the slot. And now we'll briefly look at these other two, one being universal hashing and the other being perfect hashing. So with the open addressing, the probing approaches, we did linear, just moves to that next slot that's available. You can also use a quadratic approach, which is essentially instead of just incrementing by one, you use a quadratic formula to kind of spread out how you jump around when there's a collision. And the idea is to avoid forming clusters that are too concentrated. You will get clusters with a quadratic approach still. Double hashing is an interesting way to go. So the idea there is if you have a collision, you have a second hash function that you use. And that works pretty well, actually. So that is good. So kind of this idea of any of this open addressing, any of these approaches, that load factor, if it's less than 0.7 or less than 70%, these things work pretty well. Once you pass that threshold, it doesn't work so well. So there are a lot of little practical things like that to keep in mind. And if you look at like the actual implementations like programming languages use, like how does Python or JavaScript take like your little string that you say I want to store something in and compute the hash function, they're actually pretty simple functions, and they have just kind of like magic constants in them that have been, tried out a lot and work well. So let's talk about universal hashing briefly. This is an idea, and this is about the hash function itself. We had a really simple hash function, and we'll only do, like on the exam and stuff, we're going to use simple hash functions because we need to actually be able to think about them and compute them. But when programming, we don't have those limits that we have. And so what you might want to do is, if you could get some randomness into this, is the idea. This would be great. We know we can't just do anything really random because that key always has to map the same way. But when we select our hash function, we could randomly select from a family of hash functions. And we can do that in a way that we minimize the probability of a collision. Again, this becomes, it's a little bit of math to work through to think about it. But to kind of give you one result here of an example of what you can do. So if your hash function is something like this, where you have a times k plus b, all of that is mod p, and then all of that is mod m, right? So this last mod m, we know about that. That's just keeping us in the size of our table. So the real thing we're looking at here is this hash function. So in this case, you choose a and b randomly, and they are between 0 and p minus 1, where p is a prime number that is greater than the size of the universe of keys. It's a very large prime number. We have pretty decent polynomial time ways of finding those prime numbers when we need them. So that's okay. And you only do it once, right? You only build this function at the beginning. You don't need to do this every time. And so that gives you a nice kind of property where the collision chance is very low. And that's 1 over the number of slots. So that is nice to have. So that is one approach that does work very well. You might see something like that done. I will leave the mystery of these primes and stuff to another course if you're very interested in that, because you can spend quite a while deriving that. Another method that you can use as part of universal hashing is called multiply and shift method. This one's kind of interesting because what's kind of the main driver as part of this is the bit width of the machine, so like 32-bit, 64-bit, that kind of thing. And so essentially that is worked into this formula here, which also features things like an odd integer between this and that. And I'll ask you just to trust that this is a good hash function that works well. And again, if you're interested, there is a wealth of information on a ton of different hashing functions that exist. There's also something called perfect hashing. And perfect hashing barely exists. But the idea is, if you only need to look stuff up, right? Like say you have your data set, it's never going to change, you're never going to need to delete anything or update anything, you're just doing a lookup. You can use this perfect hashing approach to build a structure that will never have a collision. And so the way that this works is to use 2 layers of hash tables, actually, to build this structure. Takes polynomial time to build it. And the benefit is obviously, it's perfect. You won't have collisions here. So speeds things up. I should mention that all of these assumptions and things that we've talked about when we talk about hashing, this is something that is called the simple uniform hashing assumption. It's not real, but it's convenient. So it's kind of this idea that each key is equally likely to be hashed into any slot in the table, and it's independent of the other keys, which is not the case usually with real data. But it's okay, it turns out, for the purposes of building these things and analyzing these things, this is fine. We can pretend this is true. And so that is just something to be aware of, that kind of all of the thinking on this is built with this assumption in mind. And it's also built with this in mind, amortized analysis. So usually we care all about the worst case. In this domain, we're more about the average here. So our big O of 1, which is wonderful, is an amortized cost. So it's over everything, averaged out. You can't like look at the individual thing because like obviously resizing the table is O of n, or, you know. So finally, I want to cover a few interesting uses of hashing other than the hash table just to store data. So if you ever used a like grep on the command line to find something, or even just like Control F or whatever to find something in a document of text, you're looking for maybe a substring within a big string. And if you think about that, that's a lot of comparisons to make if you're trying to do that algorithm. You can actually speed that up, and most software does actually speed that up using hashing. So your search term is hashed, which makes it a nice fixed size number. And then we can use a rolling hash, which kind of has this nice property of like you can slide it over the search area. And when you remove one and add one, it doesn't take a lot to update that hash. And so you can just compare the hash as you slide it across. And it speeds things up greatly. So anytime you do a Control F or something, you can think about hashing, making it fast. And this is the name of kind of the go-to algorithm. If you are interested in seeing the real implementation of it, this is just a kind of basic interpretation. Other great uses of hashing. So we're familiar with checksums for files. So we still see things like, okay, when I was like younger, everything like you didn't have app stores and stuff, right? So like you download software from a website and it would say like, here's the MD5 checksum of whatever you're downloading, so that you could check it, just in case to make sure somebody didn't like tamper with it. You didn't have like NSA or somebody making their own version and giving it to you and watching you. Hashing does that. So the idea being like you take a file of any size, you can hash the contents of that file, come out with a number essentially, and then you can compare that. So like if I build my program, I run the hash on it, I can tell everyone what the hash is. When they get my program, they can run a hash on it and make sure it matches to know it's the same thing. Obviously, in that case, if there were a collision of hashes, that would be bad. And that is indeed something that, when we talk about security applications, has been exploited before. So it's a big deal there. It's also very useful to detect corruption in a file, right? So if you run the checksum of it and it is different from what it originally was, that's a sign that something's changed. So tampering detection as well. Also duplicate detection, just a really great way to find duplicate files, right? Because the same input will give the same output, you can just run this on the whole file system and see how many copies of these things do I have. Cryptographic hashing is its whole own thing. And we should always be very careful when we get into cryptographic applications, but the idea being that when we use hashing cryptographically, we care a lot about collisions, we care a lot about things not being reversible, so when you have the hash, you can't get back to the input. So it's very useful for digital signatures, message authentication, also for kind of the way of storing passwords. Like you wouldn't store a password in plain text, but you need to be able to verify a password. Hash function is good for that. This is an oversimplification, but you can take someone's password in, it outputs a number, and you just store that number and compare those. You never know what the password is. So big use of hashing there. And kind of the last one that I want you to know about is something called perceptual hashing. And this is not, it's kind of inexact hashing, right? So we've been talking about these always having the same output, for the same input, that kind of thing. You can think about this in the sense of, like imagine you have an image, so kind of multimedia stuff is a good way to think about this. And you just like do a little color correction or something on the image. Well, the hash of the actual file is completely different, right? But you really didn't change the image that much. Like when you look at it as a human, you're like, oh, it's the same image, this one's been color corrected, right? Perceptual hashing is a way to kind of hash with some fuzziness so that you can get measures of similarity between things. This is incredibly useful. It is the way that all of the copyright detection stuff works. You know, it's why you watch YouTube videos and people do weird things like put watermarks in this way and rotate it and play it at half speed because they're trying to avoid the perceptual hash matching. And you know, meanwhile, YouTube's trying to make the perceptual hash better and better at matching it. This is the same thing. Can be used for deduplication because, like, you know, you have multiple copies of the image. Maybe it's a few pixels different, but that doesn't matter, right? And it's also used in law enforcement quite a bit. So anytime you have like sensitive material, illegal material, people will alter it slightly to avoid detection by checksum or a basic hash. A perceptual hash is used against that, so it will catch those kinds of things. So perceptual hashing is a big area of its own and kind of a fun area. And that is all I have on hashing. So I will see you on Friday, and we will talk about applying data structures.